Hello everyone, welcome to Dr. J Tech. I'm Jeffrey. The annual NVIDIA GPU Technology Conference GTC kicked off with a bang last week, and the highlight no doubt was the keynote by CEO Jensen Huang. So this time at GTC 2025, Jensen Huang shared the top 10 highlights with everyone. Today, let's dive in and break them down. So our topic today is NVIDIA GTC 2025, the top 10 highlights. First, let's talk about milestones in AI, including perception, generative, agentic, and physical AI. Next up, CUDA-X, libraries that power applications across industries. Then we have the launch of NVIDIA Halos, a chip-deployed video security system mainly designed for autonomous driving. And then comes the NVIDIA Blackwell NVL7 tool. Applications in cloud and data centers. They introduced inference optimizations for large language models like the Prefill decoding separation technique, and the NVIDIA Dynamo distributed inference service library. This time, NVIDIA also unveiled NVIDIA Photonics, its silicon photonics and co-packaged optics technology. In addition, the NVIDIA DGX Workstation series platform and the NVIDIA Llama Nemotron inference model released open source for the first time, along with the NVIDIA Isaac GR00T N1 Humanoid Foundation model. Right from the start, Jensen Huang introduced all the partners at GTC 2025, basically NVIDIA's whole ecosystem. He also showcased this year's flagship, the GeForce 5090 series GPUs, capable of creating ultra-realistic 3D scenes. Then Jensen moved on to talk about the milestones of AI, starting from 2016 when scientists first used NVIDIA GPUs to develop the AlexNet model. That marked the beginning of AI evolving into perception AI, able to understand images, sounds, and text. Then it evolved into generative AI, able to generate images, text, and audio, which dramatically expanded where AI could be used. Next came agentic AI, capable of perceiving, reasoning, planning, and executing, taking AI to the next level where it can start making decisions for humans. Ultimately, it's heading toward physical AI. Physical AI is starting to be applied in modeling physical phenomena and scientific research, and what keeps pushing AI forward is the scaling law. It means the performance of neural networks changes with key factors like parameter count, training dataset size, and training cost as these scale up or down. From perception AI to generative AI to agentic AI and onward to physical AI, it breaks down into 3 stages. The first is called pre-training scaling, where you keep increasing data size, model size, and compute tokens to steadily boost model performance. The second is post-training scaling, basically RLHF, reinforcement learning from human feedback, like getting coached by a teacher, using tests and feedback to refine accuracy step by step. Then the third stage is test time scaling, when running inference. It can flexibly allocate resources and solve problems step by step, which enhances the model's ability to decide and respond. For agentic AI, inference compute can easily jump past 100 times the old levels. Today's AI works by us providing prompts to a large language model, which then generates the first stage results. Feed that back in, get a second pass result, feed it back in again, and so on for a third pass. That style is called chain of thought. And chain of thought prompting teaches the model to reason like humans do, just like when we learned to solve math problems as kids. The teacher had us write out every step. The chain of thought lets the model imitate the whole reasoning process. But this can massively increase tokens processed, often over 100-fold. That's why token usage can explode by 100x or more. As for machine learning paradigms, first is supervised learning, where all training data comes with ground truth labels. Second is unsupervised learning. The data has no labels at all. Third is semi-supervised learning. Only part of the dataset has labels. Fourth is reinforcement learning, letting the model explore, make mistakes, and find the best answer. And the key point is when we give a prompt to a large language model, it not only generates an answer, but also allows us to verify that answer. That falls under post-training scaling. The method is called reinforcement learning with verifiable rewards, and this approach falls under reinforcement learning. To boost compute for machine learning training and inference, the top 4 US cloud providers bought a total of 1.3 million Hopper GPUs from NVIDIA in 2024 and plan to buy 3.6 million Blackwell GPUs in 2025. Each chip integrates 2 GPUs together via advanced packaging. Jensen used this chart to emphasize that GPU demand remains extremely strong, and there's a turning point for cloud data center compute. From 2022 to 2024, It was retrieval-based computing powered mainly by CPUs, that is Google's search engine. Between 2024 and 2028, it undergoes a big change, evolving into an AI factory driven by GPUs, with the market expected to reach $1 trillion. Next, Jensen emphasized again, CUDA-X libraries for applications across industries. NVIDIA has invested huge resources to help industries leverage GPUs. That includes using GPUs to simulate the laws of physics, handle data frameworks, run computer-aided engineering, and deep learning. They're also applied in quantum chemistry, quantum computing simulations, and weather analysis, as well as medical imaging, gene sequencing, and decision optimization, even signal processing applications for wireless base stations, and computational lithography for advanced semiconductor masks and numerical computing. It's precisely because NVIDIA provided these CUDA-X applications that its GPUs became the industry mainstream. AI is now applied across many industries, including enterprise IT, autonomous mobile robots and robot manufacturing. Edge 6G AI RAN for wireless access networks, that is, 6G AI RAN, as well as GPU cloud AI factories, and full-stack AI from cloud service providers offering leading tech to enable diverse apps and a rich developer ecosystem, so everyday customers can leverage CSP AI platforms to build AI applications. This includes GM using NVIDIA GPUs to develop autonomous driving technologies. At the same time, NVIDIA announced NVIDIA Halo's chip-to-deployment AV safety system, an end-to-end safety system for autonomous vehicles, integrating cloud-to-vehicle hardware, software, tools, and services to provide a comprehensive safety architecture, helping developers build and deploy self-driving cars. It also uses Omniverse to create digital twins, and Cosmos to simulate the real world, with signals detected by the relevant sensors, producing sensor tokens, then training and simulating with physical AI foundation models, and further adjusting under complex scenarios. The physical AI foundation model then generates action tokens to control real-world visuals, and feeds the sensed visual signals back to the model to make further adjustments for difficult cases, using the lower loop together with the upper loop to improve the reliability of autonomous driving, using Cosmos to predict inference images for model distillation, transferring knowledge from a teacher model to a student model. The student keeps learning the optimal trajectories until its performance nearly matches the teacher. This distillation process activates the policy model, and this closed-loop training makes policy fine-tuning actually possible. Finally, a behavior evaluator scores the driving actions, so we can gauge the model's performance. On the left is Omniverse's digital twin, and on the right is Cosmos's real-world scene generation. You can train models using both platforms together. Next, Jensen announced Grace Blackwell is in full mass production, and listed the entire supply chain involved. Ecosystem vendors building AI servers. As you can see, since everyone follows NVIDIA's reference specs, every company's products are pretty much the same. The GB200 NVL72 rack system for data centers includes 10 AI servers on the top row, 8 AI servers on the bottom, and 9 NVLink switches in the middle. All of this is wired with copper interconnects. A total of 5,000 copper cables, with NVLink cable length adding up to 2 miles. Jensen also stressed this point. To make more GPUs work together, you need to scale up communications inside the rack, which is about adding more bandwidth inside the rack for communication. It also involves scale out, which is about boosting communication bandwidth between racks. He also showcased AI servers and NVLink switches on stage. For the GB200 AI server specifically, each unit uses 2 superchips, and every superchip combines 2 GPUs with a CPU via advanced packaging. Everything is liquid cooled, so you'll see the inlet and outlet water pipes. NVIDIA's Blackwell NVL72 AI server, including 72 Blackwell GPUs, 576 memory chips, 18 NVLink switch chips, a total of 130 trillion transistors, 2,592 Grace CPU cores, and 72 ConnectX-8 network interface cards, plus 18 Bluefield data processors. Especially for the NVLink switches, they allow many GPUs to work together, handling massive numbers of tokens. Next, let's quickly go over what a token means. A token is the basic element of text. It can be a word, a character, a symbol, or even smaller. It depends on the model's tokenization strategy. In other words, different companies define tokens differently. Tokens are the basic units a model uses to understand text. The model converts text into a sequence of tokens, and then based on those tokens it computes, generates, understands, and responds. In other words, it's the chatbot's answer. Tokens are also how cloud AI platforms charge through their APIs. And prompts can't exceed the token limit set by the model. So whenever we use a cloud AI platform, billing is always based on tokens. Each language model has a different token count. On average, one token equals about 0.85 English words or 0.5 Chinese characters, and the word count varies depending on the text. For example, GPT-3's max output is 2,049 tokens, roughly 1,000 Chinese characters or 1,700 English words. GPT-4's max output is 32,768 tokens, about 16,000 Chinese characters or 25,000 English words. As for how many Chinese or English words equal how many tokens, you can check this website. It shows how OpenAI's model actually splits tokens. Artificial neural networks, also called neural network, are mathematical models inspired by the structure and function of biological neurons. They're used to evaluate functions or approximate computations. The circles you see here represent signal strength and the arrows represent amplification, which are the weights, also called AI parameters. In this neural network model, A1, A2, A3, and W1, W2, W3 are all floating point numbers, so the computing power of GPUs is measured by their floating point performance. For example, the Llama 3 large language model has 400 billion parameters. That corresponds to 400 billion arrows, 400 billion weights, 400 billion Ws. And training means turning text, video, images, audio into floating point numbers A1, A2, A3, then feeding them into the neural net, repeating weight calculations W. That process is called training. Once training is finished, you end up with 400 billion floating point weights W, the trained parameters. Then you can use this trained model to run inference. Inference means converting images, text, or sound into floating point numbers A1, A2, A3 and feeding them into the trained model. Through those 400 billion trained weights W, it calculates the probability of an event happening. If applied to generative AI, the unit of neural network computation is the token. Here's a real example. Let's say we ask the chatbot a question. Here's the question written in Chinese. A traditional large language model would use 439 tokens for inference. A newer reasoning model would use 8,559 tokens for inference. That's 20 times more tokens and 150 times more computation. On the left is the traditional large language model. For example, Llama 3.3, which has 70 billion parameters. It runs with a dense transformer model on 8 H100 GPUs. On the right is the new reasoning model like DeepSeek R1. It has 671 billion parameters, with 37 billion active at a time. It uses a sparse mixture of experts model running on 16 H100 GPUs. Using the traditional large language model with only 439 tokens, the final inference result was wrong. But using the new reasoning model with 8,559 tokens, the inference result was correct. Next, let's talk about inference optimization for LLMs, specifically the technique of prefill decoding separation. In traditional LLM inference, prefill and decode are usually handled by the same GPU. Prefill is compute intensive, meaning it requires lots of processing. Decode is memory intensive, meaning it needs lots of memory access. If both run on the same GPU, they'll compete for resources and slow down performance. Since the prefill phase is C-compute intensive, when traffic is high or prompts are long, meaning the questions are long, the prefill phase creates heavy computational load. The results are temporarily stored in the key value cache, KV cache. The decode phase is memory intensive, because each token that's generated needs frequent access to data stored in the KV cache. So preserving cache data is key to speeding up inference. That's why NVIDIA launched the Dynamo distributed inference library. When a user asks a question with a prompt, it first goes through prefill, saving results in the KV cache. Then Decode generates the required tokens, which are assembled into an answer for the user. So Prefill and Decode are separated. It uses different GPUs to handle the computation. Dynamo is basically the operating system for an AI factory. It mainly helps users run disaggregated inference, GPU resource allocation, KV cache routing, and communication libraries. Here are some of the companies using NVIDIA Dynamo. Training means feeding data into computers, finding rules, and building a model. So, a model is essentially the rules of the data. Inference means putting new data into the model to predict the future. Large-scale inference is extreme computation, which means it requires massive processing. In this chart, the x-axis shows tokens per second per user input. The y-axis shows the total tokens per second a data center can handle. With fewer users, the data center can process more tokens per second. With more users, the data center can process fewer tokens per second, whether it's GPU flops per second, or high bandwidth memory bandwidth, or software and architecture. The overall direction of AI development is clear. The response speed needs to get faster and faster, and the number of tokens processed has to keep growing. That's how data centers can boost their revenue. And NVIDIA Blackwell's inference performance takes a giant leap. Here, the x-axis shows tokens per second needed by a single user. The y-axis shows a megawatt-level AI cloud data center and the tokens per second it can handle. With Hopper processors, the tokens per second are limited, but with Blackwell processors and NVL8 servers running FP8 computations, a megawatt-level data center can handle much higher throughput. If you use Blackwell processors with NVL8 servers running FP4 computations, since precision drops from FP8 to FP4, the tokens per second keep increasing. If you use Blackwell processors with NVL72 servers, basically scaling up the servers while running FP4, the tokens per second increase even further. And with Blackwell processors plus the Dynamo library together with NVL72 servers running FP4, it lets a single user's tokens per second increase even more. Compared to Hopper processors with the Dynamo library, we can see that using Blackwell processors with the Dynamo library, the tokens per second can maximize data center revenue. This is what CEO Jensen Huang wanted to emphasize. Using Blackwell processors with the Dynamo library, leveraging NVIDIA's platform for inference computing, lets data centers achieve maximum revenue. Meaning using NVIDIA GPUs is better than data centers developing their own ASICs. And with NVIDIA's latest Blackwell processors and the Dynamo library, they can run TensorRT LLM deep learning inference software. For 1K incremental speech language models and 2K online speech language models, Blackwell delivers 25 times computing power of Hopper. For 32K incremental speech language models and 8K online speech language models, Blackwell delivers 40 times computing power of Hopper. So, a 100 millihour AI factory using H100 NVL8. There are 45,000 GPU chips and about 1,400 racks, processing around 300 million tokens per second. If switched to GB200 NVL72, there are 85,000 GPU chips, but only 600 racks. And the tokens per second jump to 12 billion, from 300 million up to 12 billion. That's a 40 times increase in token revenue. So Blackwell delivers 40 times inference performance. This echoes what Jensen Huang once said, the more you buy, the more you save. Now it's the more you buy, the more you earn. Meaning if data centers adopt Blackwell, they can make more money. Next, let's talk about digital twins of AI factories. Using the Omniverse platform to build AI data centers. That includes power management and cooling efficiency. Engineers, whether design, network, mechanical, or electrical, use development tools, simulation data, and scene data, using general scene descriptions to generate application hosting on both cloud and on-premises, and such a digital twin system lets vendors review anytime. And users, AI engineers, can use this platform to train AI models with agent models and NVIDIA Inference Microservices (NIM) through a physical state controller. They can simulate the whole AI data center's operations. This picture here was built using Omniverse Digital Twin. It's a simulated AI data center environment, and NVIDIA's next-gen Blackwell Ultra NVL72 will enter mass production in the second half of 2025. It'll deliver 1.5 times performance of the previous GB200 NVL72 with 2 times instruction. The Blackwell Ultra chip uses 2 reticle-sized GPUs. It delivers 15 petaflops of compute, especially for FP4 dense matrix computation. It comes with 288 GB of HBM3E high bandwidth memory. A full rack provides a total of 20 TB of high bandwidth memory and 40 TB of fast memory. That's 1.5 times the previous gen. And it supports 14.4 TB per second ConnectX-8 Ethernet. Its switching capability is 2 times the previous generation. And its rack uses the same Oberon cabinet design as before. NVIDIA's next-gen processor is called Vera Rubin NVL144. It will enter mass production in the second half of 2026. It delivers 3.3 times the compute power of the previous GB300 NVL72. Vera is the CPU. It has 88 custom ARM cores and 176 threads, with 1.8 TB per second NVLink chip-to-chip. Rubin is the GPU. It uses 2 reticle-sized GPUs and delivers 50 petaflops of compute. For FP4 operations, it supports 288 GB of high bandwidth memory, HBM4. Each rack supports 13 TB per second of HBM4 bandwidth and 75 TB of fast memory. That's 1.6 times the previous generation. It also supports 260 TB per second NVLink 6, which is 2 times the previous gen, and 28.8 TB per second ConnectX-9 Ethernet. That's also 2 times the previous generation, and it still uses the Oberon cabinet design. And the next-gen Rubin Ultra NVL576 will enter mass production in the second half of 2027. It delivers up to 14 times the compute power of the previous GB300 NVL72. It uses the Vera CPU and the Rubin Ultra GPU, the 4 reticle-sized GPUs, delivering 100 petaflops of compute. For FP4 operations, it supports 1 TB of high bandwidth memory, HBM4E. Each rack provides 4.6 PB per second of HBM4E and 365 TB of fast memory. That's 8x the previous generation. It supports 1.5 PB per second NVLink 7. That's 12 times the previous generation, and 115.2 TB per second of ConnectX-9 Ethernet. That's 8 times the previous generation. And it uses the new Kyber rack design. Servers are placed vertically. In the Oberon rack design, servers were placed horizontally. In the Kyber rack design, servers are placed vertically. This increases density and allows more servers. And NVIDIA's Rubin NVL144 uses a total of 576 Rubin GPUs, 304 memory chips, and 144 switch chips. That's a total of 1,300 trillion transistors, 12,672 CPU cores, and 576 ConnectX-9 NI, plus 72 Bluefield data processors. NVIDIA's fast roadmap drives the AI factory economics. From Hopper to Blackwell to Rubin, performance has scaled massively from 1 to 68 to 900. Compute power is leadership, and total cost of ownership (TCO) per unit of compute has dropped dramatically. Hopper to Blackwell to Rubin, from 1 down to 0.13 and now 0.03. That means TCO per compute unit has fallen to just 3%. NVIDIA also launched Spectrum-X Enhanced Ethernet. It powers the world's most advanced AI clouds and factories. On the left, you see Spectrum-X Super NICs. On the right, Spectrum-X Ethernet switches. And below, the supply chain partners involved. NVIDIA still follows the scale-up approach, meaning copper is used inside the cabinet. For scale-out, which is outside the cabinet, fiber optics are used between cabinets. Next, let's look at NVIDIA's silicon photonics and co-packaged optics. This is InfiniBand using silicon photonics. Quantum-X will enter mass production in the second half of 2025. On the left is Ethernet using silicon photonics. Spectrum-X will enter mass production in the second half of 2026. And NVIDIA's silicon photonics and co-packaged optics are developed in collaboration with ecosystem partners, providing 1.6 tera silicon photonics with co-packaged optics, along with new micro-ring modulators. A modulator basically turns an optical signal into light and dark dark for 0 and bright for 1. It also uses TSMC processes for 3D stacked silicon photonics engines with high power, high efficiency lasers and detachable fiber connectors. Over 100 patents have been licensed to supply chain partners. This means NVIDIA's silicon photonics and co-packaged optics are designed to be detachable. When the laser fails, you can detach it. That perfectly solves the problem. Normally, co-packaged optics can't be replaced, since lasers have a limited lifespan. Using detachable optical connectors fixes the issue of failed lasers that can't be removed. Over 100 patents have also been licensed to supply chain partners. Below is a list of NVIDIA's silicon photonics and co-packaged optics partners. This is a Quantum-X optical switch built with NVIDIA's co-packaged optics. Here is the interposer. This is the core of the whole co-packaged optics design. It includes electronic ICs, EICs, and photonic ICs, PICs, using advanced packaging to 3D stack electronic and photonic ICs. It uses microlens surface coupling plus fiber connectors to link optical fibers, forming an optical subassembly. It also uses external laser source modules and laser source packaging. What you see here is the switch management module. The yellow part here is copper, so this is a liquid cooling system, cold water in, hot water out. This is the Quantum X800 ASIC. Basically, it's an InfiniBand switch chip. It provides 28.8 terabyte per second, built with 107 billion transistors on TSMC's 4 nanometer process. It delivers 3.6 trillion 8-bit operations per second, and it uses in-network computing technology called Scalable Hierarchical Aggregation and Reduction Protocol, SHARP. This computing enhances the switch's performance, and this here is the co-packaged optics chip. It has 324 optical connectors, 36 laser inputs, and 288 data links. It also has built-in fiber management. Here you see 3 modules, each outputs 3 optical fibers. That's a total of 18 optical fibers. When you remove the cover, you'll see 3 detachable optical subsystems inside, each with a silicon photonics engine. Together, they deliver 4.8 terabits of data transmission. If we zoom in on this part, you can see inside one of the silicon photonics engines, there's a 200 gigabyte per second microring modulator. It reaches 1.6 terabyte per second data rate. That saves about 3.5 times the power. This transparent piece is the fiber array unit, FAU. It's basically V-grooves etched into glass or plastic. Then the fibers are placed into the V-grooves and glued together with epoxy, basically strong adhesive. So fiber array units aren't exactly groundbreaking high-tech if we cut open the silicon photonics engine to see a cross-section. On top are 3D stacked photonic integrated circuits, PICs, and electronic integrated circuits, EICs. Below that is the interposer. The very top transparent piece is the fiber array unit, FAU. Zooming in on the silicon photonics engine, it contains about 220 million transistors. Built with TSMC's 6 nanometer process, it has 1,000 integrated photonic devices. At the top here is the electronic integrated circuit, EIC, and this one is the photonic integrated circuit, PIC. Finally, the fibers are routed outside the switch. Using a multi-plane optical connector, a total of 1,152 single-mode fibers are linked. They come with automatic temperature tracking and wavelength and power stabilization. When the temperature rises, the laser color, that is the wavelength, usually shifts, so it's important to keep wavelength and power stable. This is NVIDIA's Quantum-X silicon photonics InfiniBand switch from the outside. It has 18 external laser sources and 144 MPO multi-fiber push-on connectors. This is what the connector looks like. It can hold many fibers at once. One switch uses 446 billion transistors. It provides 115 terabyte per second of data rate. NVIDIA's optical switch is the world's most advanced co-packaged optical switch. Quantum-X Photonics will go into mass production in the second half of 2025. It's an InfiniBand switch with 144 ports and 800 giga data rate, or 576 ports at 200 giga data rate. Spectrum X Photonics will go into mass production in the second half of 2026. It's an Ethernet switch, offering 128 ports at 800 giga data rate or 512 ports at 200 giga data rate. There will also be larger scale switches with 512 ports at 800 giga data rate or 2000 ports at 200 giga data rate. NVIDIA is rolling out a new platform for AI factories. It evolves from Blackwell and Rubin using the Oberon rack architecture to the next generation called Feynman. It will use next-gen high-bandwidth memory, the Vera CPU, the 8th gen NVIDIA switch, and Spectrum 7 with up to 204 tera co-packaged optics, plus the ConnectX-10 switching chip. And it shifts to the Kyber rack architecture. NVIDIA will reinvent the $500 billion enterprise IT industry for the age of AI, including AI infrastructure for compute, networking, and storage, plus the AI operating system called Dynamo, which runs all kinds of AI applications on top of it. NVIDIA launched the DGX Workstation series. The smallest workstation platform, you can see its size compared with a laptop. Another one in the DGX Workstation series is the DGX Station. It uses the GB300 Super chip with 784 GB of unified system memory, 20,000 teraflops of AI performance, and a ConnectX-8 Super NAI. Here are the related supply chain partners. So NVIDIA is offering AI infrastructure for enterprise computing, from the smallest DGX Spark to larger RTX Pro and DGX Station, to enterprise servers like RTX Pro and DGX B200, and even the DGX GB300, which can deliver up to 15 exaflops. Meanwhile, leading storage vendors are building AI data platforms for enterprises because AI requires handling huge amounts of data. So, storage servers are absolutely critical. This includes enterprise file and vector databases. Through generative AI microservices, they run the Llama Nemotron model. On the right, you can see a server that integrates both compute nodes and storage nodes. Here are the related supply chain partners. So Dell plus NVIDIA provide the industry's broadest end-to-end AI enterprise infrastructure. It covers AI PCs, Spark, Station, compute servers, networking servers, and storage servers all the way up to Blackwell compute racks. They have over 2,000 customers and more than 100 newly released products, delivering over 49 exaflops of performance. At the same time, CEO Jensen Huang announced that NVIDIA's Llama Nemotron Inference model is open source. It's a large language model distilled, quantized, and optimized by NVIDIA, with 49 billion parameters. That's compared with Llama 3.3's 70 billion parameters and DeepSeek R1 Llama's 70 billion parameters. NVIDIA's Llama Nemotron Super has higher agent task accuracy along with faster tokens per second performance. Next, NVIDIA showcased many related partners, including Accenture, Amdocs, AT&T, BlackRock, and Cadence, Capital One, Deloitte, Ernst & Young, and the Nasdaq exchange. SAP, ServiceNow. These companies all use NVIDIA hardware and software platforms to develop AI. Finally, CEO Jensen Huang talked about robotics as the next trillion-dollar industry. That includes simulation, deployment, and training. Future humanoid robots will help people with chores at home. According to a three-stage scaling model, humanoid robots are now in pre-training scaling and post-training scaling. That means using internet videos to pre-train AI, while also training AI through human demonstrations. Finally, through post-training with synchronized data generation and reinforcement learning simulation, their humanoid robot functions are enhanced. NVIDIA uses physical AI and digital twin operating systems, namely NVIDIA Omniverse, to build virtual worlds with digital twins. Together with NVIDIA Cosmos, they simulate the physical world to generate massive data sets. These two platforms are used together to train humanoid robots. At the same time, NVIDIA and Disney Research, along with Google DeepMind, published Newton, a scalable physics engine to enhance robot learning. Together with MuJoCo, Disney Research, and custom software, they released NVIDIA Warp as an open-source framework. It's used in Python to generate data and perform spatial computation, forming a framework for robot learning. This works together with the ISAC robot software development platform. MuJoCo itself is a contact-rich multi-joint dynamics with contact, a general-purpose physics engine. It's used in robotics, biomechanics, and machine learning software development. At the same time, NVIDIA introduced the Isaac GR00T N1 Humanoid Foundation model. Users can give prompts to the robot. For example, pick up an industrial item and put it into the yellow bin. That text gets converted into text tokens. Meanwhile, the robot's sensor input signals are converted into sensor tokens. Through vision language models and diffusion transformers, they're converted into action tokens. Finally, the humanoid robot carries out the related actions. In summary, at NVIDIA's 2025 GPU Technology Conference, 5 major announcements were made. First, Blackwell is entering full-scale production. Second, the Blackwell NVL72 Dynamo operating system can deliver 40 times the inference performance. And Rubin, NVIDIA's Silicon Photonics, powers AI infrastructure. In addition, AI infrastructure will expand into the $500 billion enterprise IT market as well as robotics-related applications. Lastly, let's wrap it up. This time at NVIDIA's 2025 GTC, the main focus was to emphasize how AI has evolved from decision-based AI to generative AI and further toward agent-based AI, with the future even reaching physical AI. And right now, in the field of agent-based AI, we can now solve problems using chain-of-thought reasoning. In the past, generative AI used fewer tokens, so the error rate in answers was higher. Now, with chain-of-thought, a single question can be broken into many smaller steps. That makes the number of tokens go way up, but accuracy improves too. We've mentioned before, will AI eventually hit a bubble? The key is to watch when chatbots can stop sounding smart but making stuff up. So chain of thought is one solution. But using more tokens means you need more compute power. That's why CEO Jensen Huang emphasized this time that AI inference in the future will keep demanding more and more compute power, all to make AI more accurate. That's it for today's program. If you have any questions about generative AI, agent-based AI, or NVIDIA's AI computing platform, feel free to leave them in the comments section below. We'll discuss them together. Thanks everyone, good night, bye-bye.
Mm-hmm.